Hi there. So I've chosen coffee roast preference prediction for my project, and I've actually worked on this solo. So I just want to give you an intro to my problem background and the context. So I follow this YouTuber named James Hoffman, and he's essentially like the MKBHD of coffee. So he's a reviewer, and his opinion on coffee is very respected in the coffee space. And so a few years back, he performed this really big, like distributed taste test where he mailed out like 5,000 tasting kits all across America, along with like an online survey. And so just to give you an understanding of what this might look like, he essentially mailed out four like coffee pods that were unlabeled because it was a blind tasting. And so people would heat these pods up with water, and they would do a blind tasting. And so they would then describe the notes that they believed were in the coffee. They would rank them. They would, try to measure the acidity and brightness just based off taste. They'd also enter in details about their age, their spending habits, and other sorts of demographics. And so from this, James Hoffman, he created a YouTube video where he aggregated all the results and kind of showed some charts and did some data analysis, um, just kind of showing what are the general trends. But he didn't really apply machine learning to the data set at all. So that's kind of where the motivation for this project kind of began. I wanted to discuss and kind of figure out what were the most predictive factors that go into predicting someone's desired coffee roast level. Now I just want to give you a primer on coffee roasting to begin with. So raw coffee is actually green. And so as you start the roasting process, we're kind of brought to light roasts, which are essentially very floral. They got these bright acidic notes. And some people tend to like them, and some people really don't like the acidity. Now, as you roast longer, you kind of reduce that acidity and you bring out these like warm, chocolatey, almost nutty notes in the medium and medium dark roasts. And then as you go longer and hotter beyond that, you kind of get like a smoky, charcoaly taste because we essentially burnt the coffee. And that's why dark roasts are so black. And so we'll get to this later with the model training, but there's kind of a big class imbalance, and there's sort of a bias in the coffee community towards light roasts because a lot of the like special and nuanced flavors that are in a coffee bean will be destroyed in the roasting process. And so people tend to prefer light roasts in general. And so that's what I wanted to predict. So people they've stated their desired roast level in the survey, just in general, like not including the coffee samples because those are blind samples. And I want to figure out that based on their opinions of those four samples, can I figure out, what the factors go into predicting their ideal roast? And so there's no medium dark roast category in the actual data set. So we're just going to be focusing on predicting the target variable, which is going to be light, medium, or dark roast. So now I wanted to describe the data set that James Hoffman actually released. And this is the raw data set. So this is before any feature engineering, and this is just what I found on Kaggle. So really features of importance, I would say, are things like age, the number of cups you drink, what is your brew method? Like, do you use espresso at home? Do you do pour overs? Also things like, if you add milk or sugar to your coffee, do you have like oat milk? What kinds of additions do you have? And then here are like the rankings. So people kind of describe the notes they found in the blind samples. And they also try to like measure the acidity or brightness. And then finally, which of these four samples you actually prefer. And then we get into things like spending habits and how much are you willing to spend at a cafe or on your own equipment at home. And then there are less important features like your ethnicity, employment status, political affiliation, which maybe could have some predictive power, but as you see in the paper and in this presentation, there's not really much. So now we'll get into the pre-processing section. So I do some sort of exploratory data analysis where look at like nulls. I sort of start categorizing the features into whether they're like ordinal, nominal, numeric. With survey data in general, it tends to be that most of it is subjective and therefore categorical because one person's five is not the same as another person's five. So that was a really big challenge in dealing with and building a classifier for this, and we'll get into that in the model training aspect. Now, I do some mapping of just like simple types of like just trying to convert strings into numeric types. Now, one thing that's revealed in the YouTube video is that of the blind samples, coffee A was a light roast, coffee B was a medium roast, coffee C is a dark roast, but also coffee D is a light roast. And so you'll see that inherently in the data, there is a class imbalance because it's not, it's not one to one. And that's generally the case of all like the coffee community. There are more specialty beans that are light roast than are medium or dark roast. And so I wanted to preserve this class imbalance because I think that it's still important and still indicative of the actual domain. And also, there was only about 4,000 rows of data. So I felt that removing rows to force a class balance was not going to give me better performance. And you'll see that actually later down here, I'll show the distribution. Now, stated roast level is what people say that of like the roast that they actually like, and this is not including like the blind roast. This is just like the blind samples. This is just uh, like what people like in general. Now, you'll see that most people like light roasts, and there's a good amount of people who like medium roasts, but no one really likes dark roasts. But I don't think this is a big enough class imbalance to really do anything about. There is still data in the fact that less people like dark roasts. And so that's why I kept that. Now, I want to get to the feature engineering. So I'd say the most important features I added were probably is purist. Now, this is a feature where I essentially am trying to determine if someone is drinking coffee for the taste or just kind of like for caffeine. Now, the idea here was that if someone is not drinking, if someone is not adding milk and sugar to their coffee, they're probably trying to taste some sort of nuanced flavor or complex flavor in the coffee. And so I would consider them to be a purist. While someone who's adding additions to that, they're almost kind of like masking those complex flavors. And so I would consider them to be like not a purist. And so this is like a Boolean field. And I've also added these new fields called like brew skill features. So I've considered the brew methods that people use at home and how much attention and skill they require. So, for example, brew high skill. If someone's brewing espresso or pour over at home, that requires a lot of time, attention, and money, and it's not really easy to get into. And so that's why I've created a high skill category. Now, there's also a medium skill category. Now, this is for coffee brewing machines where you have to put in ground coffee, or if you're drinking French press or you're doing cold brew, I would say that is requiring less attention and skill than espresso or pour over, but it's not as little as, for example, instant coffee or Nespresso pods, which you see I've categorized as low skill. And so you'll see that these are actually very predictive features, and that people who are drinking instant coffee are usually less likely to care about the taste of the coffee as opposed to someone who's drinking espresso. And that's because, simply the time and the money they've invested into it is usually correlated. So now to get into the training section of this video, I've actually trained 4 models in the dataset. 3 of them being decision tree based models, which is random forest, cat boost, and XGBoost. And then I also trained a really simple neural network on this, which is just a multi-layer perceptron, just because I wanted to have at least 2 architectures against this data set, just as a comparison. So to get into I do some standard pre-processing, scaling, imputing. I also use this function called select kbest, which essentially does an ANOVA F value test against the individual features independently against the encoded Y labels. And that's because we want to determine what are the best features to actually include in our set. And here I'm just taking like the top 25 of these ANOVA F values. And so we go from like 43 features after the pre-processing to 25. Now, for the split, I just do a standard 80-20 split, and I stratify with the actual target variable because, like I mentioned before, I want to keep that class imbalance. I do think that there's some information in that. And also, I only have like 4,000 rows. So I don't want to remove more training data because already, neural networks, for example, have an issue with like overfitting on small data sets. So I really don't want to remove observations from this. So getting into the training code is all pretty similar for each model. I do grid search on all the tree-based models, and I determine the optimal parameters. And then I do k-fold cross-validation where k is 10, so I do 10 splits. And then I basically just train the best model from the grid search on that. And then I collect my metrics. My metrics are accuracy, precision, recall, F1 score, and ROC, AOC. And then I also output a confusion matrix. So for XGBoost, I'll just go into the actual results. You'll see that the results with the tenfold cross-validation and the test salt is pretty similar, roughly around 0.69 for all the metrics. And the classification is the best for light roasts. You'll see that there's just generally more data for light roasts, but also it just performed the best. If you look at precision, this class label number one is light roasts, like 0.80, 0.78. While with medium roasts, it's not that bad, but it's still worse. And then with dark roasts, there's just like almost no data. And so just probably most likely overfit and just learn noise. Now, the most important features. So it's interesting to note that the actual blind samples, the roast level from the blind samples that was a person's favorite, was a really strong predictor in determining their stated roast level, which I guess makes sense because if that person really does have like some sense of coffee expertise, they would most likely know what they're tasting and be able to recognize that. Also, if the person likes fruity notes or chocolatey notes, those are also really good predictors because, like I mentioned in the video, fruity notes are generally associated with light roasts, and chocolatey is kind of with like a medium roast. So you'll see like the style notes features are really important out of those 25. So Cat Boost is pretty similar to XGBoost, except it's a little bit more tuned for categorical data, which survey data in general, like I mentioned, is subjective, and because of that, it's categorical. Now you'll see, I do the same exact process: grid search, k-fold. Now the metrics are also very similar. So you'll see that performed the best for light roasts, did the worst for dark roasts. But interestingly, the revealed roast level was also the best, and the fruity notes were also, very important. And age and expertise were also useful, indicators. Now, finishing off with the decision trees, we do the same thing for random forest. And I'll show you the confusion matrix, and it's almost identical in terms of all the results. And we get roughly 0.6768 for our metrics. Again, light roast is the best, dark roast is the worst. And here, fruity actually performed as like the best indicator. And again, expertise and age are also very valuable. Now, moving on to a different architecture, the neural network. This is just a multi-layer perceptron where I have a hidden layer of size 128 and then 64. And I get into all the metrics in the paper, but you'll see that it performs significantly worse. Just looking at this confusion matrix, it gets the light roast a little bit worse off, but it gets the dark roast like worse and the medium roast worse. And so that kind of brings the entire model performance down when you actually combine these metrics. So these are hovering at around 0.61 or so. And so it significantly underperformed the decision tree models. So I think that's an interesting takeaway when we compile the results here. You'll see that Boost performed the best, but by a very slim margin. Random Forest and XGBoost did pretty much the same thing. So I think, if you minorly change some parameters, you could probably get one of them to edge out the other. But in general, Boost did do the best, and the multi-layer perceptron did the worst. So it's interesting to note that on this kind of task, for this small data set that's noisy, tasting, data, decision trees generally outperform neural networks.